Many of them talk the mathematical basis of neural networks, and you can delve yourself into it. Remember, a number of these books were written for computer scientists and for mathematicians. We don't like that many algorithm code or these things. There were some which I really liked. This is Simon Haykin's, which cover a good details. And then there is Neural Network Design. This is a free book which is available by Haga and so. And I really like this interaction because it goes fairly basic works. There are some others which I have found to be comparatively easier to follow for my students, and I would recommend the same to you guys. I'll just jump into this. I've already covered this. Okay. Now, what our nervous system or any brain would do, it will take a stimulus. The stimulus will be translated into an electrical signal, and it will go to a neural network which will do something with it. Okay. The thing which does something with it is this. We don't know how it works. Okay. Let's be very clear. We know which part of the brain does what. For example, our visual cortex is here, our auditory cortex is. So we have labeled various parts of the brain as Brodmann areas, but we don't know how they actually work. What we do know is it has many of these inside it, the neurons, which have got kind of a structure like this. It has got a central body, a long tail, and then few other connections. So they talk to one another. What we also know is we have a large number of these, got roughly 10 to the power 11 neurons, right? And they're densely connected. Each neuron is generally connected to 1,000 or 10,000 other neurons. They talk densely with one another. But the other problem which we know is that they are very slow. The speed is roughly of the order of a millisecond. Okay? How fast are our logic gates? We've got few gigahertz clock speed, right? And we are saturated actually. We have stopped ourselves at 3 gigahertz. We could easily make a 10 gigahertz clock speed further. We just don't know what to do with it. The question then comes is, how does a machine which is working in millisecond does all this computation? Whereas we working at gigahertz are still finding it difficult to do. I mean, you guys can hear my talk and ignore half of what I'm talking. You are doing that. You have to do that, or else you cannot store all that information. Right? You are seeing to my scene and you are ignoring half of what you are seeing. And your brain is immediately thinking, nah. A poor computer has to record all of this, compress all of this, and then extract information out of this. So we compensate for our slow speed by massive parallelness. It's way more parallel than our common gates are. Our fan out is of the order of 3, 4, 10. Right? Here, each gate is connected to a large number of these. We also have a 100-step rule in neurons. Computation does not take more than 100 steps in our brain. This is primarily due to power requirement, power and time. If we can't decide within 100 steps, then we are in trouble. Many of our algorithms take much more than 100 steps to do that, any operation. Okay? The other thing which we don't know how it works is, remember I told you neuron is connected to many other neurons. The amount of information they share is actually very, very low, at maximum few bits. So when you are seeing a picture, it would have been taken by roughly 100 million odd pixels. It goes to 11,000 cortical neurons going to the brain, where these neurons extract few bits here and there, and they're trying to make a picture. So we don't know how that works. How do these gates, only sending few bits of information with one another, are able to do this complex operation? The other thing is, the brain is very plastic. It's not a hardwired computational machine. We are born with some hardwired structure. Rest of it will learn with time. right? Our eyes, I mean, when we are born, we can only see till about 1 hand distance. We start seeing with due course of time, we recognize features. We're not born with language and other features, okay? So that's how our brain does. Let's see what is a neural network. So by now you guys should know what a neural network is. I'm sure you have heard enough of this word in your undergraduate, postgraduate. What is a neural network? Every system has input and outputs. So how is a neural network different from a normal system like op-amp? No, you can have a neural network with one layer. Multiple hidden layers will be a deep learning system. If we have one or more inner layer, that's a deep learning system. Okay? The definition, if you take Alexander and Morton's 1990 definition, would be something like this. It's a massively parallel distributed processor which has a natural propensity for storing. It can store information. Okay? It stores experimental knowledge. It kind of resembles brain that it acquires knowledge through some learning process. We did not say it learns the same way the brain does. Okay? It's similar, it has got a learning process to learn. And then the storage is through the intersynaptic weights. The weights are between two different individual neurons here. That's where the storage is. That's the only similarity between our neural network. Well, you can try to, but most neural network and human brain have that common feature. They learn somehow, and whatever they have learned, they stored in memory between two individual blocks. Now, we need to start to make a network, we need to start with a neuron. Okay? And this, many of you might have already seen. A typical perceptron or a neuron looks like this. It takes n number of inputs, multiplies these inputs with weights, which are my stored memory elements, adds up all those weights, and then there's an activation function which judges, are these some function more than a threshold, less than a threshold, or they are in particular, there will be a function which will give kind of an output, which will be a compressed output. Okay? And based on whether my output does what I want or not, if it already does, I don't do anything. If it doesn't do, if there's an error, I then go back and update my weights. The theory is if I do it a large number of times with known data, I will learn how my input data is related to my output desire. The activation functions could be, I mean, you could have just a step activation function. If the sum data is below a certain threshold, my output is 0. If it is below, my output is 1. Or you could have a tanh or a sigmoid kind of function. Have you seen a function like this in electrical circuitry before? This or that? Sorry? Okay, is there an electrical circuitry which can give me this response function? Remember, all of this I'm training on how to make these. We are hardware people. Actually, an inverter kind of have an output like this. Yes, to 0 it makes 1, 1 it makes 0, but it doesn't do a sharp change. There's always a smooth change. Right? A differential amplifier current has got a response function like that. Okay. Top of that, we will have a simple feed forward network where data just moves in forward direction. And if you place an hidden layer which neither sees data from input nor sees data from output, you have got kind of a deep learning system. In modern days, of course, we have large number of these hidden layers and we have got some form of optimization to do this. And we kind of have a two-way flow in these layers. The function flows in forward direction, the error propagates in backward direction, and you propagate the error and try to do this. So how many of you already know the operation of perceptron? Do I need to teach how it works, or you're happy how it is trained, so that I can jump into making these? The head shaking. Translate this in English language. You know it, you don't know it. You don't know it. Fine, that's perfectly fine not to know. Right? As I said, if needed be, I will go very fundamental and then we'll go proceed. Okay, then let's try to make a perceptron in next 15 minutes. That's what my own teacher has asked me to stop. Let's see how far we can go. So let's take a very simple system. I'm taking the simple system from the book which I mentioned earlier. I want to make a single learning system which classifies between two inputs. So all I want to do that, I've got a assembly line production system where fruits are coming in, okay? And I want a neural network. I've got tons of sensors which measure various properties of these fruit, and I want a neural network to identify whether my fruit is an apple or a banana. Now, as a human observer, we know immediately if it's an apple or banana. But remember, what's the IQ of computer? 0. It has no inherent knowledge unless you teach it. So that's all I want to do. I want to sort this thing into banana box and apple box so that I can put all the bananas on one side, all the apples on one side. A very simple problem. Okay. Now let's think. We have got 3 sensors which we have placed because we did not know what we are measuring, right? Priori, the system has no idea about its input. So let's give 3 types of sensors we have. One which looks at the shape, one which looks at the texture, and one which looks at the weight. Okay? And all it says, if the shape is round, I will give an output of 1. If the shape is elliptical, I will give an output of -1. If texture is smooth, output of 1, rough, output of -1. Let's take weight of 1 kilo. Weight more than 1 kilo, output of 1, less than 1 kilo, output of -1. At this point, your brain will immediately say, hey, that weight sensor is not needed. There's not going to be a banana more than 1 kilo or an apple more than 1 kilo, but I did not know that. As a neural network, I have no idea about that. I need to teach myself that. Similarly, I mean, if you would say immediately, the only sensor needed is a shape sensor. Unless you get a round banana. Do we get a round banana? Or an elliptical apple? Slim chances. Okay? So, in ideal world, my banana, the sensor output will be -1 for shape, it's elliptical, 1 for texture, it's smooth, and -1 for weight. And my apple will just have 1 for shape, 1 for texture, and -1 for weight. Okay? So that's my input criteria. I need a neural network to identify based on these 2. And remember what we did, our neural networks are generally things like these. They take all these input matrix, whatever my sensor have measured, multiply the weight. So whatever weights are saying, how important is this sensor data for my classification? Now you would immediately say the only data which is important is shape. Everything else is less important. But I don't know that right now. I need to learn that these 2 are not important, this is important. Right? And this I can learn by giving something. Okay, give me some apple, let me see if I can predict it as an apple. If I don't predict it as apple, then let me go and change my idea of how the world is. Okay? So essentially we are doing this. We have these measurement vectors, we multiply them with the weights of each one of them, and we add an offset. Why we add an offset, we will see in a short while. Okay? So let's take an example. So if that was my weight, my ideal weight vector is this. Okay? So -1 times -1 is 1. These 2 will become 0. If my output is 1, it's a banana. -1 times 1 is -1. If my output is -1, it's an apple. So that should be the ideal weight vector which I need to learn. That's what I need to store. Only consider this, don't consider these two. So when I initialize the system, I don't know about it. So I need to learn that. Okay? So you can do apple and banana test like the way I did just now. Okay. If you give it an orange, that system will not work, right? Will it work with an orange? Because maybe your texture will become rough here. Now let's go through the theory of learning the weights. Now of course the theory is a bit more convoluted, but we are doing a very simple example. So our neural network has got only one perceptron. Okay, we are training it with a single perceptron system to identify between these two. So we are doing something called supervised learning, wherein we are telling to the neural network, this is the right reply. Okay? For this input, this is the reply I expect. We are doing it for some set of data. Okay? And we are also doing something, there is something called reinforced learning, wherein we don't give examples, but the network grades itself, how good I was, how bad I was. Okay? And then there's also something called unsupervised learning, where we are just classifying. I have got a set of input. Can I divide it into two groups? Okay? Telugu speakers versus non-Telugu speakers. Okay, that kind of thing. So let's start with, I'll first teach you the theory of how learning happens. And my eye is on the watch to see if I can go quick and finish it in 15 minutes. Should I finish it in 15 minutes, or you want to have a slow process and we also learn it properly? I can finish the whole thing in 15 minutes, that's not a problem. Slow process. Which means you'll have to hear me for the whole second half as well. You're happy to hear me? Okay, somebody's happy. So the way it happens is, let's take the example of a 2-input perceptron. Okay? So for each set of input, I will have these. What is my measured vector and what is my desired output? What's my measured vector? What's my desired output? Measure vector, desired output. Okay. Was there a bell ringing somewhere? So you start with random initial weights, because we don't know what the weights are. Which sector is important, I don't know. You start with random initial weights, and then you start with the first input. Our first input here is 1, 2, expected output of 1. My random initial weight is 1 and 0. Okay? So I multiply these two together. So 1 times 1 is, that's my 1 times 1 would be 1, plus 2 times 0.8 is minus 1.6. Now sum together becomes 0.6. And the kind of activation function you are using is a hard limit activation function. Anything below 0 is 0, anything above 0 is 1. So my output now becomes 0. My desired output was 1. So my network is wrong. Okay? What's my error? Error is 1. Okay? So now I need to go back and change my weights. I've done a wrong prediction. Now there are many ways you can go back and change your weights, and all these help on how quickly the neural network gets to the most optimum weight. Here we will take a much simpler approach, which is, if my error is 1, my error is 1 here, right? I just add whatever was my input vector. Okay? All I do is I take the weights and add my input vector to it. Because if my error is high, its chances are high that there's some important feature which I am missing. So I started with 1, 0. I just add these weights to it. As simple as that. I get a new weight here. I don't know whether this is right or wrong. So what I do next, now let's pass the second set of data to it and see whether after adding these weights have I got my true weights or not. So once again I have got -1. Now these are my new weights, 2, 0. So multiply 2 with minus 1, 1.2 with 2, I get an output of 0.4. Hard limiting function gives me an output of 1. Still wrong. Okay? So initially, what's my error now? 0 minus 1. My error is minus 1. So what I could say is this is causing an error in the other direction. These inputs. So rather than adding, this time I subtract it. So I subtract the weight and I get whatever is the old weight, I subtract my input vector from that. So if it's pushing the error in that direction, I add it, error in this direction, I subtract it. I'm doing a very simple operation here. Okay. So I get new sets of weights, 3 and 0.8. Let's try it with the third set of data. Do anything to weight. If not, if my desired output is less than my actual output, subtract the weights, otherwise add the weights. Alternatively, if I do it in a more mathematical fashion, all I am saying my new weight is my old weight plus error times my input. Okay? And same thing I am doing for my bias as well. Now bias is nothing but an input signal where the signal is always 1. Okay? So that's the mathematics behind it. Let's try to see whether it works for my apple banana problem. Oh, I am going to finish it in 15 minutes. Is it clear till now? Speed is okay? Okay. So once again, I have 3 sensors now. Let's see if this thing works. I mean, previously we just trained it, right? Let's try to train it. So why don't I start with a random initial weight again? And this is what you guys can practice on your own. You can give any random initial weight and see if the thing works. So we have started with 0.5 minus 1, 0.5. It's no way related to my desired weight. My desired weight was minus 1, 0, 0. Just far enough away from that. Okay? So and I started with initial B of 0.5 as well. So that's my input data set, minus 1, 1, set of 1. I apply this thing again here. So minus 5 into minus 1 is, sorry, 0.5 into minus 1 is minus 0.5, minus 1 into 1 is minus 1, 0.5 into is this. I get a result of 0.5, I get an output of 0, I should have desired an output of 1. I am erroneous. When I have got a desired of 1, what I do? I just add the data there. Okay? I get new sets of weights. I do the same thing with the second set of data, and this time my output is 1, but I should have got a response of 0. My error is minus 1. I train it again. I reduce this number back to it. I'm aware I'm going a bit faster here, but I'm doing the same operation now. So once I have got, after 2 iterations, I have got new sets of weights here, which is minus 1.5, minus 1, 0, minus 0.5. Now one thing you would have seen, only in 2 iterations, I went from, my initial weight was 0.5. I need this number to be minus 1. I went from minus 0.5 plus 0.5 to minus 0.5 to minus 1.5, very close to my desired thing. I know these two have not become 0, but we also know they are kind of immaterial. This alone is almost equivalent to sum of these two. Right? So I have come very close to my desired iteration in just 2 sets of iteration. And you can do that with a check. So I now check it for, say, one of the other features, the banana feature, minus 1, 1. And hey, that gives me 1. So in 2 training epochs, I train my single neuron to identify between apple and banana. Still takes longer than the time it takes to train my 3-year-old daughter. Apple, banana, and she will be doing apple to everything after that. Everything is an apple. And the same thing works for banana as well. So I give 1, 1, minus 1. Same vector, minus 1 in 0.5 into 1 is minus 1.5. This becomes 1, so cuts out, that becomes a hard limit of minus 1.5. I will get a result of 0. I finished a 2-hour lecture in 15 minutes. That should be good to me. Now, despite the simplicity of this training, I have taught a very simple training system, right? I'm just adding and subtracting. It will always converge to the actual weight if the weights exist. And there lies the beauty of this thing. Okay? A neural network is, of course, more than a single neuron. It's a network of such neurons. Now, hopefully by now you know how the basic building blocks works. Okay? In the second half, we will do more on how to make these physically. Okay? Unfortunately, we don't have the Cadence lab today, or else we would have made this network in Cadence. That's not very difficult to make. Okay? We ended up with 3 weights and 3 input vector. That's it. Okay? But we'll still see how we can make it. There are few things which are needed here. We need a multiplier. Do you guys know how to make multipliers? Electronics people, some of them should know. How do you make multiplier? There's head going up and down. So next question is, tell me the answer. How do you make multipliers? So what are the operations I'm doing here? I'm essentially multiplying 2 numbers, adding the 2 numbers, and then defining 0 or 1. That's all I'm doing. This is what we will try to do. We'll try to find the simplest way to multiply 2 numbers, add the 2 numbers, and then hope for the best. Okay? We're not going to be able to make a whole big neural network on a chip in 2 weeks workshop, but hopefully we can make a single neuron. Okay? We stop for now. Good, okay? नहीं पढ़ना चाहिए. Okay. So we left morning trying to understand how a perceptron works. Now from our point of view, a neural network is nothing but a repeated combination of same building blocks. Okay? So same perceptron repeats. How it trains, how it grows, that's least of our concern. Of course it's of our concern as well, but because that consumes space, area, and all those things. But we will now see how we can make this, or how at least we can try to make it. Okay? We'll see many different approaches. So this is what we need to make. Okay? So what are the things it does? Do I have a stick? Where does the stick go? Or a projector? Yes, thank you. So what we have here is n number of inputs. In the morning when we designed our perceptron, we just had 2 inputs. Right? Now we have n inputs which are being multiplied to n weights. Okay? And then they are being added. So we have multiplication here, we have summation here, and then we have an activation function. These are the few things which we need to build. There are many ways to do this. You can have a purely digital neuron, in the sense that you could code it in Verilog, VHDL, try to compile it on an FPGA, and so on and so forth. The question then comes, where do we store the weights? Now you see, the highest amount of energy consumption in an AI system is not in multiplication, not in addition, but in memory fetch. wherever you are storing the weights, the time it takes to go there, take the memory and come it back. Now the reason why it is that, traditionally computers were designed to be, just give me a second. So you might have seen a block diagram picture, something like this, in your first year computer science lecture, so electronics lecture, what we call as the block diagram of a computer. So that was one of the earlier machines, the Harvard architecture, which tries to have the memory in two parts. There is a data memory and there is an instruction memory. Now whenever you are doing a digital operation, you are doing something on some data. That something is your instruction. Previously the instruction memory and data memory was kept separate. But the architecture which became very popular is the Princeton architecture, or the von Neumann architecture, which tries to have a common memory for both, or has a common memory for both data and instruction. Now, and then you have data moving from input to output. Now what has happened over the period of time, processors have kept on becoming faster and faster. We had the Moore law. Memory is also kind of becoming faster and faster. Not at the same pace, but it is becoming faster. But the thing which is not growing at the same pace is the connection between these two. The interconnect speeds have not grown too much. So we now have what we have been having this for about 2 decades now, what we call as processor memory bottleneck. So processor is fast, memory is fast, the interconnect is not very fast. Now this is another figure which I often talk about. So because of these microelectronics, I said in the morning, we went from machines which are this big to machines which are tiny. Our machines do not learn. Our hardware is not meant for learning. The traditional hardware is meant for running a program. You write a program, it runs the program. Now this is a slightly older result. This was, I think, almost a few years now, when Google Brain project came up. And the idea was to identify cats in YouTube videos. To do that, the system took 16,000 processors and used 100 kilowatt of power. My daughter can identify cats in YouTube videos on a piece of bread. Not just one YouTube video, she can show videos after that and she will identify cats. Right? To some extent, it is because of the way we are writing code. So we hardware people have provided processor at a very low price. Earlier, the processor and memory was costly. We had big machines. So our software colleagues were nice in writing software. Now we have provided for cheap. They are being a bit liberal. So this is the performance memory gap which we see in processor and memory. If you look at the scale of improvement, these are not on any particular scale, but if we start with 1 in 1980, whatever was processor and memory at 1980, by how it has improved over the years, we have got a significant improvement by the time we reached even the last decade. Memory has also grown. You can see we have gone from 4 MB to 256 MB to 2 GB and so on and so forth. Now we are having multi-GB memories. But the gap in the performance has kept on increasing. Okay. One of the reasons for this gap in the performance, the devices themselves are performing slower, and second is we need to have data moving from CPU to memory and back. And for these we have buses which are off-chip systems, and buses are slow. To find solution to this, we started having cache memory. On the processor, we started putting memory, and we tried different levels. There's level 1 cache, level 2 cache, and so on and so forth. Now that system worked pretty fine, except when we are looking at a neural network, for every operation which we are doing, I need a memory fetch. I need to bring what was my weight. So think of it this way. I have a 1000 layer deep network. Each layer has, say, 100 neurons, each neuron with 10 inputs. A very simple configuration. So already for overall number of weights is 1000, which is 10 to the power 3 into 10 to the power 200 into 10. So we're looking at 1,000,000 memory fetch just for one instruction. Okay. That causes problems. One could ask, why don't we build the memories then and there itself? Why don't we make a memory at the site? Now historically, the way we have designed memory is the same way we have designed cameras. We have designed memory as an array. We designed one memory element and we designed an array of this. So next part of this might be a bit simple for advanced students, but I was told that they are earlier students, so I should go a bit more simpler today. Let's see how do we make adders and multipliers. So we need to add and multiply, right? So how do we make adders in digital logic? You two should know this, right? So if I add two numbers, if I just do a half adder, so 1 and 1 added will give me 1 0, 0 0 will give me 0. The sum becomes an exclusive OR. A full adder is these two numbers plus the carry from the previous stage. So it's an exclusive OR. The carry is a majority gate. It selects either AB or BC or CA. Okay. So we can implement this in this circuit. I mean, that's a simple implementation. I've done the XOR gate as simple as one can, and you can do the C out there as well. This is multiplying 2 bits. 2 bits with so this is adding 2 bits with a carry. Can somebody count the number of transistors we have? And make a note of it. So if we have that many counters for addition and just addition of 2 bits, we would generally have 8-bit data. How many bits are your machines? 64-bit machine, just to make our life very easy, right? So let's assume all of our weights are also 64-bit and all of our input is 64-bit. So how many transistors will I need to make the adder? Let's keep track of this number. So I would really want you guys to count the number of transistors. Don't worry about whether they're NMOS or PMOS. Let's count the number of transistors. And please make a note of it. This number is going to exponentially rise if you're just right. So my majority gate needs 10 transistors, right? And XOR 16, is it? So I need 26 transistors just to make 1-bit adder. My end customer wants 64-bit precision. So 64 into 26 is what I need just for addition at one terminal. So at here. Okay. Now of course you could say, why don't we use the same adder for all of them? Of course we could do that. We could have the same adder and multiply and do it in sequence. That will just make a system a bit slow, but for the argument's sake, let's just go that we are making neural network as it is. Okay. So 64 into 26, we are looking at something like 900. 1664. Oh yes. So I have spent 1500 transistors in making one adder. And we decided to make a network which is 1000 layer deep, 100 layer on each node and 10 input, which is a small network, right? So we had 1,000,000 neurons in our network, right? So we have 1,000,000 adder needed. So 1500, let's take, I know 1600, but let's take a ballpark, easy to, so 1600 times million, right? We are already at 1.6 billion transistors. Doable? We are putting 100 billion transistors on a chip, right? So it's not impossible. I can do that. I have only done addition till now. I have not done multiplication. My apologies, I was wrong. We don't need the addition at each stage. So my brain is dead. As you can see, second half of the day the brain stops working. That's the adder. That's the multiplier. Right? So we're designing the adder till now. So I don't need an adder for each stage. I only need adder per number of. I still need 1600 times. I said 100,000 layers, so 10 to the power 3 to 6. So 1,000,000 adders I will still need. Okay. So that was the easy bit. Subtraction. How do we do subtraction? Complement. No. We do 2's complement, not the 1's complement. By itself is 1's complement, right? What's 2's complement, second year students? Sorry? So invert everything, add 1. Okay, good. And I'm sure you can prove that 2's complement is actually subtraction. Okay. What's 10's complement in decimal number system? So if you're subtracting 3, you can think of it as, how is another way to subtract 3 from a number? So 5 minus 3, if I don't have a subtractor, how will I add it? I will add 7 to it and remove the 1. 5 plus 7 is 12, right? And if you remove the 1, I get 2. So 5 minus 3 is 2. So this rule of 2's complement works in every base system. In base 10 system, we have the 10's complement. Okay? Good. Now can somebody tell me how do you make multipliers in digital logic? Sorry? Shift and add, because that's what the next slide says. And that's what we learned in our high school, right? The way to shift and add is and then add them up. Which means I now need to compute all these partial products, each number multiplied by each number, store it somewhere. And even just I'm doing a 4-bit adder, I need 4 shift registers to store these individual numbers and then add them. Actually, each shift register now becomes an 8-bit shift register. Okay. So essentially my operation becomes something like this. If I have got a large number of bits, I need all the bits stored in shift registers and added. That does not look very area nice. It will take quite a lot of area to make. Right? We just looked at adder and that was taking a lot of area. There are also people who do array multipliers, but it will remain the same thing. Now, how many of you have been taught the concept of Booth multiplier? 2 people, so you can teach us the Booth multiplier. Come on, tell us what Booth multiplier is. Circular and shift. Okay. So for the second years who haven't come across Booth multiplier, we will do it very quickly and you guys can close your ears and eyes for some minutes. The multiplier concept comes from very simple. If you have to multiply a number by 10, what do? You just put a 0 at the end. If you want to multiply a number by 100, what do? You put 2 zeros at the end. That's a simple concept. So if you have a series of zeros somewhere, you don't need to actually multiply, you just shift the number. Right? By putting 0, I mean if I have 12, I'm putting 0, I'm just saying I'm just shifting 12 one side and putting a 0 there. Agreed? Now how do you multiply with 99? So multiply the number by 100 and subtract the same number. Okay? So you could do same in binary logic. If you're multiplying a number by 1, 1, you can multiply it by 1, 0, 0 and subtract that number. Okay? The first part is easy. Multiply by, put 2 zeros. Second part is add that number, add the 2's complement of the number. Okay? So one thing which we could do, sorry, we're not going to do this thing here. Remember, we are looking with signed bits. Okay, so the first bit is denoting it's a positive number or a negative number. So one thing which we could do is we could look at these factors. We could look at group of numbers. If I have got a long sequence of bits to be multiplied, rather than multiplying it all at one go, I look where there are sequence of zeros or ones. And sequence of zeros, wherever I do, what I do? I just add zeros later. Sequence of ones I have, it means I add zeros and then subtract that number from that. That way I can reduce my computational complexity of multiplication. Okay. There comes the concept of Booth multiplier, which goes by this very simple algorithmic approach. If you get, and we're just looking at 2 bits at a time. Let's start with it. We can also, there are also 3-bit Booth multipliers. So if you get pairs of zeros, just shift the number. If you get pairs of 1, still just shift the number. Don't do the subtraction right now, because we will only do subtraction when we get 0 or 1, because that seems that 1, 1, it might be pair of 1, 1 and then there could be another pair of 1, 1 there. Okay. So when you get 1, 0, that's the time you subtract and shift. So you add the 2's complement of a number. When you get 0, 1, you add and shift. So you will get something like this. Okay. Okay, here's another example when we are multiplying 13 by 9. You can just sequentially add and shift, add and shift, add and shift, and in the end you will get a result. Okay. Okay. I'm not going to in details because Booth multiplier is taught in most undergraduate courses. So even those who haven't come across this, you will see that in due course of time. It's also well known, if you have a number which is continuously frequently changing 0, 1, 0, 1, 0, 1, Booth multiplier is not a great multiplier because it goes to the worst case scenario. Other thing worth remembering is you don't need to just do 2 bits, you can do a 3-bit sequencing as well. You can do modified, because if you're multiplying with 1, 0, 0, you just, that looks like multiplying the number by 4. Okay. So let's go back and see what we are doing in Booth multiplication. Now what do we need to make a Booth multiplier? We need an adder, right? When we are saying subtract, we are adding the 2's complement. So we need an adder circuit. So a 64-bit adder is needed as well. Okay. I also need something to shift. So if I was multiplying to 8-bit number, I will need a 16-bit shift register because the result will be 16-bit. So I'm multiplying to 64-bit numbers, I will need 128-bit shift register. I need a control logic which looks if it is 0, 0 or 0, 1, something to look at that, a comparative logic. And I need a place to store the number as well as its 2's complement. So if nothing else, I need a 64-bit adder, a 128-bit shift register and a bit more control logic. 64-bit adder, we counted the number of transistors it needed. 128-bit shift register, how do we make shift registers? By D flip-flops. Anyone remembers how many transistors a D flip-flop needs? Around 15, at least 10, certainly not less than 10. Let's be generous and only give 10 to it. I think it's around 20. Depends upon how you, whether you design using pass gate or you design using. So the bottom line story is, we would we would burn about 3 to 5 billion transistors in making this neural network. We have not yet implemented the training scheme. Remember, in the training scheme we needed to look at the output, take the difference, and then go back and update my input. So even before implementing the training scheme, I have burned a large number of transistors making this neural network. Then the other thing is this memory. What kind of memory can I have? So what kind of memory cells do you guys know? What kind of memory do you have? Be loud, guys. Primary, secondary. Okay. Okay, RAM, I know. What kind of RAMs have you heard? SRAM, DRAM. Okay, good. Well, now we have got noise in the classroom. What are DRAMs? What are they physically? Transistors. Well, transistors are used to access them, but most DRAMs are a capacitor. Right? It's essentially a capacitor which is holding the charge. But DRAMs are not typical capacitors. They are special purpose capacitors. Remember, the way we make them, for making capacitors you need a parallel plate. Right? If you saw the chip early morning, we had loads of parallel plates, but they were not big enough. So to make DRAMs, generally what we do, we drill a trench in the silicon substrate and then fill it with conducting material so that we get a big capacitor. If I get time, do remind me to show you some SEM images of DRAMs. Which means DRAM are actually, even though they are good memory, they take a very small area, it's just a capacitor. They cannot be built in every process. They have specialized process to make DRAMs. Okay, and actually below 14 nanometer process, DRAMs are not really being very successful. So we're using quite a lot of SRAM, yes, but DRAMs not. Now what's an SRAM cell? Have you come across an SRAM cell like this? So it's essentially two inverters back to back. So we have got the output of one inverter connected to the input of one inverter and the output of this connected to the input. So it's basically a inverter which keeps on regenerating its own output. And we have two access switches which are there to read or write. So that's for 1 bit. If I have 64 bit reads, I need 64 into 6 of these as well. You can immediately see that is not feasible on a chip. A deep network is very difficult to implement on a chip. A shallow network, yes. A small network, yes. The other problem which we have is we are actually camera designers. We thought we can have a neural network with the camera and then you can do anything in the real time. Right? Take a picture and tells you what the picture is. But my camera is already taking a large amount of area. We had already a large number of pixels. We have already got a large number of diodes. On top of that, I have to make these. It's very difficult to put them on a chip. So, yes, the industry is doing this quite a lot. There are a lot of people who are working on a digital deep neural network implementation on a chip, and there's a lot of work going on, don't get me wrong. I would like to argue that whatever you do in digital processes, the number of cells needed will still remain large, and hence so many cells will also consume a lot of power. Each of these, we haven't talked about power till now, each of these gates are consuming power. Even though in CMOS we say there is no static power, actually there is due to leakage. Dynamic power will always be there. Okay. So let's now go and see how do we make this neuron in analog technique, and is that actually any beneficial? Because I still have the same problem. I need to add, I need to multiply. So how do I multiply in analog? At the end of the day, I'm going to be very tired because I have to stand the whole day today. How do you multiply 2 digits in analog things? Yes, resistance is a good multiplier. It multiplies 2 things. That's not the only multiplier we have, do we? There are a lot of physical equations which try to multiply 2 quantities. Okay? So he talked about using the Ohm's law, which basically multiplies voltage with conductance. Okay? So in our configuration, we have no shortage of such laws which multiply 2 numbers. We can have tons of multipliers. The other beauty is resistive multipliers don't need each bit multiplication. They are doing it all at one go. Right? But we don't like resistors. Few reasons. They're difficult to make. And we are making things small and small and small. And now you will come back and give me a 10 kilo ohm resistor. That will take a bit of area. They're even more difficult to make uniformly. Because you're not only asking for one multiplier, you're asking for a million multipliers. And the worst of that, they carry current. Current flowing through resistor gives power, I square R. Right? So whatever I do, they will carry the, but they still do a very good job. Now how do we make, so we can possibly use resistors for multipliers. How do we make adders? How do we add to signal in analog? This has been taught even to first year students. Do you remember op-amp based addition? Like 2 resistances, 1 resistor, and that adds 2 signals, right? So remember, when we are doing this voltage based multiplication, we are getting a current output, right? Our output is current, so we need something to multiply, and that we have seen in undergraduate. So if we have tons of current, all of this pass through a op-amp based circuit, we will get adders. Okay. The question then comes is of memories. Not only I need a multiplier and adder, I also need something to store my data. Okay. So when the last time, artificial intelligence have had summers and winters. And by summers and winters, I mean sometimes it has been very popular, the cool thing to do, and then people stopped working on it completely. So it's not a new term which we are using. In 1960s, when computerization started for the first time, people thought, well, we have got an intelligent machine and AI is going to come and take all our jobs. 10 years later, it died. In 1980s, we had things called artificial neural network, ANNs, which were spiking neural networks. And once again, people thought, oh wow, cool, they can solve all these problems. And then they did this thing. 20 years ago, we started with this deep learning convolutional neural network bandwagon, right? Has it started dying already, or is it still going on? How many software engineers did Google and Meta fire in last 2 years? You guys don't read those news, right? You only read how many people got jobs, not how many people lost their jobs. So what happened about 5 years ago? See, industry works like sheeps. So everybody thought AI is the solution to everything. So a lot of engineers were hired. And now all of a sudden you realize either it consumes too much power, it does too much training, there's not enough data. It's good for centralized people like Meta or ChatGPT to come up with something, but not necessarily terribly good for all the simpler problems. So all of a sudden you're not going to have AI based people for doing this thing. The reason why I started talking about history of AI was last time when AI was cool, the way we were making memories were these. flash memory drives or EEPROMs. All of you have used them, right? Do you know how they work? Has it been taught to you in your undergraduate? In your graduate studies? No? So the way these devices look like, they look like transistors, but rather than a single gate on top, they also have a floating gate in between. There's a second gate here. This gate is not connected to anything. So same source drain, there's a gate which is not connected, and then there is a top gate which is connected to something else. Okay? The idea is, by using tunneling operation, if I apply a high voltage here, some charge will tunnel through this dielectric and come on this thing. Okay? That charge staying there changes the threshold voltage of the transistor. If I want to remove it, I apply high charge to the body, and this charge comes to the tunnel through hot electron tunneling and then goes away. So that's how you program and discharge a flash gate. You're essentially, in the digital EEPROM devices which you have, it is essentially storing two values of threshold voltage. And if you remember your MOS transistor, you change the threshold voltage, you change the current output. Okay? So the threshold voltage can be used as something to store memory. Now you might ask, why only two values, 0 and 1? We can certainly store many different threshold voltages. Some of those who have done MOS design, what was the typical threshold voltage of your transistor? 0.6, 0.7 volt. So I don't have big headroom to change it dramatically. Right? So a lot of work actually has been reported in literature where people have used these memories to make neural network. But the interesting thing about these memories is the neural network would be this big on the chip. The control logic to control would be this massive right next to it. Because now you need to provide high voltages, right? And you're talking about a 3.3 volt technology, you're talking about 15 or 16 volt to apply. So you need charge pumps to produce that voltages. So brilliantly works, can be used, but cannot be reproduced, cannot be done with a large number of these things. This leaves us within a trouble. We can make multiplier, we can make adder. Our memory solution is not terribly good, particularly analog memory solutions. And this is where some hope lies in new type of memories which are coming up. A lot of it is in the research domain. We are also writing papers on that. Most of these new type of memories are not based on circuits. They're not transistor. Remember, all the memories which we talked till now, they're transistor based. Right? SRAM was transistor based. DRAM had a capacitor, but still transistor based. Flash has got a floating gate, still transistor based. And this is where the problem lies. Virtually every foundry think their memory would be the one which will take the market. Remember, memory market is huge. And the whole reason okay, not whole, but I believe Samsung became such a big company because their memory business started flourishing. Okay. So number of memories which are there, and these are the words you will hear quite a lot. There is phase change memories, who change their phase, and phase could be resistance or optical condition based on applied heat. Okay. There is magnetic memory. In magnetic memory you have things wherein you are using a spin and orbit of magnetrons or the torque in the tunnel. You have resistive memories whose resistance changes by doing something, by applying a voltage or by applying heat or giving energy. Somehow you give the energy to the system. You have ferroelectric memories which are kind of magnetic based. You have oxide replacement memories. You have conductive bridge RAM. And sometimes, like conductive bridge RAMs, many times are similar to RE RAMs, but because of industrial pull and push, they are all being called different names. So every foundry has got their favorite, or they have got 2 or 3 of their favorite, hoping one of these will succeed in market. So right now in the stage wherein we don't know which one of these will succeed. The other issue is, remember, they're not transistor based, they're physics based, they're device physics based. So how they will scale? Transistors, we know, as we made the transistors smaller, the memory also started becoming smaller. How will these scale is an open question. So we are in that flux where a lot of neural network work is going on based on these new type of memories. We don't know which one will succeed, if any one of them will succeed. Okay, so with that warning that maybe none of them will click, I'll just introduce one of these to you because physically they are beautiful devices. Okay. And that's the devices called memristors. So ignore whatever is written on the circuit. So you knew things regarding voltage, current and charge. You know these three things? So the relationship between voltage and current, there's a fundamental material called a fundamental element of electronics engineering called the resistance, which relates between voltage and current. Okay, there is capacitance, which relates between voltage and charge, and of course between charge and current you have the time based relationship. We also have inductance, which basically relates between flux and current. So when we say d phi is L di, now flux was kind of one of the most ignored things when we learn. We don't talk much about flux in our undergrads. We know what it is and then very quickly move to L di dt, don't we? So Leon Chua argued that if I put them all in a kind of a rectangular block, I have a relationship between this and this, I have a relationship between this and this, I have a relationship between this and this. So there has to be something which relates charge and flux as well. There has to be the fourth fundamental element. And he predicted it will be a memristor. It will act like a resistor, but it will also have a memory. It will remember its past states. So formulation wise, it's just d phi is equal to m dq. For a long period of time, Chua predicted its existence in 1970. It wasn't seen. It was one of those theory paper which was good to read, but no one had seen this. HP was able to show similar behavior in very thin stacks made of metal oxide. So if you had two conducting layer on top and you have metal oxide in between, they saw similar behavior. The beauty of these devices is you apply high voltage, their resistance changes, but the resistance remain that till you apply a very low voltage. Okay. Now we have been trying to make now the devices work fairly okay, they are still not stable. Nobody has been able to make a million odd memristors. Remember, in order to make a neural networks, we'll at least need a million memristors to put the weights. We are also making them. We can barely make 16 by 16 arrays, small arrays of memristor. The other issue which has happened with memristor is again which material do we make of. So typically memristors are formed of 3 stacks. Again, I will bring some pictures tomorrow to you guys. So essentially the kind of memristors which we make, they have a top active layer, a metal layer, and a bottom layer. In between we put a dielectric. So otherwise it looks like a capacitor. Okay. Now if you take a very thin dielectric, it will have a high resistance. Right? It will have, and all capacitors have a resistance, it just have a fairly, and the layer thickness we are talking of is a few tenths of nanometer. Okay. Now what we have seen, what other people have seen before us, is that if your top layer is made of some metals, so in our case copper, silver, molybdenum, okay, and the bottom layer is neutral, all it does is provides a contact, it doesn't do anything. So we can make platinum or ito or any metal you want. So if you have a thin, say dielectric, something like silicon dioxide or amorphous silicon, and you have a thick layer here, you apply a certain voltage, what happens is these ions start moving in this dielectric. Okay, do I have a, oh this is tied here, I can't remove it, but okay. So as ions start moving in, so you have copper on top and copper ions are slowly moving into the dielectric. If you keep on applying high voltage, at some point they go and touch the bottom electrode. Now as you can see, what has happened is I have formed a channel of copper ions. copper ions channel will have low resistance. So something which had high resistance, by applying a voltage, it has now resulted in low. Even when I remove the voltage, these ions will not travel back on their own, because this is a solid structure, right? So ions will not travel back. Now I have got a low resistance state. The only way to remove the ions will be to apply a high voltage to the bottom layer and negative voltage to top layer, so that all the ions get attracted back. Okay? So this gives us two resistive states. Now by applying high voltage, I mean 1 or 2 volt we are talking about, right? So 1 or 2 volt of positive voltage forms the channel, 1 or 2 volt of negative voltage removes the channel. And I will show you some examples in one of our later lectures. Now the reason why this device is interesting, it is a resistance. For when I am not charging, when I am not applying high voltage of 1 or 2 volt, if I am applying 0.5 volt, it is a resistance. Okay? Which means it's a multiplier. Okay? The other thing is, I can change its resistance value. So when I am programming it, I can apply a high volt and shift its resistance. The people have also tried doing pulse and giving many resistance values rather than just a low resistance and a high resistance. You can have multiple resistance states in between. Which means we can make something like these crossbar arrays, wherein, say that's my input signal V1 to so on. These can be multiplied with this memristor, plus it's the same current. So current in series gets added. This can be multiplied, current in parallel gets multiplied with this resistor, this can be, and then we can feed this to a summing amplifier at the end. So and rather than designing each neuron, we just create these large arrays of memristor and then go and program each, because in a neural network, the same input will be fed to many different neurons. So that way you have got, if that is the output of one neuron, this is to the second neuron. So conceptually they are very nice devices. They appear to be potentially the future of neural network design, and if we can make them, if we can stabilize them, the problem with these devices is they are not stable. They still take programming. You still need a programming circuit to put high voltage or low voltage to make them work. There is massive variability in these. Every 2 memristor behaves very differently, and order to stabilize are still up in progress. So people like TSMC are trying to do it, but it's still very early stage. The problem of power consumption is still not very solved. They say these are consuming less power than our equivalent of digital logic, but the moment I use resistance, current will flow through resistance, right? And we will have power dissipation going on. So the only way to reduce that, because remember what we are doing, we are applying voltage across a resistance. So voltage is my input. So how do I reduce the power dissipation when I apply a voltage across a resistance? I can either reduce my voltage or I can increase my resistance. So V square by R. So if I can make, the problem which I have is the moment I make the bridge, I get a very small resistance. Okay. So the research direction which people are taking now is how do we increase the dynamic range of these resistors, how do we change the resistances so that we get lower power. So conclusion for the first 45-minute odd of the lecture is that the classical von Neumann computer, which you have been using for so long, makes very cheap and powerful machines. You all have a von Neumann machine with you. But they are not the ideal machines to implement neural network or artificial intelligence circuit. We can make a neural network out of digital circuitry which is available to us. Analog seems to do better job at this point of time, or at least looks to be doing better job at this point of time. It still has got all the issues of noise, variability, reproducibility, and those are still very high research topics for us to play with. But it is promising that if you're going down the direction of machine learning or neural network based systems, we might have to revisit the entire digital design the way we do it, or else power is going to be a big concern. Or else what might happen is we never go to, so you know how we went from large machine to personal machines. If we don't solve that problem, we will never have personal neural networks. So that is a research direction where a lot of work is going on right now. We don't have any solution yet. So we'll take a break now, and when we come back from the break, we have done 2 or 3 things today. We have looked at lumped parameter models in the morning. We have looked at neural networks. So why don't we do some exercise problems? So in the second half we will do some tutorials. Okay, I will come around and help you guys. We'll set the problems on the board, and then we'll do the tutorials, because if I do another lecture, you guys will be dead. Right? There's only so much lecture we can hear in a day from a same person, and there's only so much lecturing I can do. I mean, I can talk another hours, but my brain is already dead an hour ago, and it's a day for fasting for me. It's Purnamashi, so I haven't ate anything. But so I think it's better we do some tutorials. Tomorrow morning I have been told the lab will be available, so we'll be now. Okay, before I let you go, so there are 2 things which we should have discussed about. One is neural network designed and trained, but there's another approach which is happening in research. Why do we need to constantly learn? So if a neural network has been trained in cloud or trained in data center, can't we just physically make that trained neural network with those parameters? Okay. If we have to do that, then we don't have to learn, we don't have to change the resistance, we just build finite resistances in the chip. Okay. How can we make resistances in the chip? So one is memristor. Say our process does not have memristor. What other ways we can make a resistor? We can make a long wire, that's a resistor. It's a small resistance. Or we can use a transistor. Remember, transistor operation goes up and then flat lines. The time it is going up, it looks like a resistor. It is a resistor. It's a voltage dependent resistor based on the gate voltage, and I can change its resistance slightly by applying different gate voltages. Okay, so we can use a transistor as a resistor. So one thing which we could try doing tomorrow, those who haven't done the image sensor, it will be a good idea if you guys go and do your pixels. Those who have done the schematic of the pixel, I will sit with you and we will do the layout, because layout is fun. And if you reach even that stage, then we'll try to make a perceptron, a simple neuron using purely transistor, no memristor, nothing else. Okay, good. Let's take a quick break now.